in the lab in various capacities. So I'm really excited to get to this milestone. So Shriniwas, please go ahead.
Okay, so I'll just jump straight in. So you want to start? Okay.
Right. So, if you want to plug in your laptop, it's 28%.
It is? Oh, sorry. Thank you for that. It just looked out.
There you
go. Okay. Thank you. Okay. All right. So the title of my dissertation is an investigation of multisensory feedback for prosthetic control. Before we get into prosthetic control, I'd like to talk a little bit about how non-prosthetic users use their hands. So all of us have hands, and we realize that using our hands is a multisensory experience. So whenever you try to use your hand in the environment, you use your eyes, your sense of touch, your ears, you hear for your interactions. So, the object properties can be sensed even through that, and an internal model of you sort of have an internal model of what you're doing and what your hand is doing in space, and the sensory perception from that as well. So you can see that it's a very, it's not a sort of just a one unidimensional problem. There's a lot of things that go into controlling just your able-bodied person's hand as it is in the environment when interacting with objects. If you try to think of this like an engineering system in terms of a block diagram, you can think of sort of the brain that has downstream, there's a spinal cord that have two-way communication between the brain and the spinal cord, that has again two-way communication between the muscles and the spinal cord. You have the same between the muscles and the hands. When I say hand, I mean the actual movement that is happening at the in the fingers. Then you have some environment which in which you're moving, interacting with objects. That interaction then leads to visual and auditory information going back to the ears and the eyes, back to the brain. You originally had efferent neurons that were pushing the signal to the muscles, but you also have afferent neurons that are carrying the haptic information back to the spinal cord, then onto the brain, and so on. But like we discussed, using your hands is a multisensory experience, but so is using a prosthetic. It should be no different. Essentially, if you think of the limiting condition where you want the perfect prosthetic, it should ideally replace your hand as it was when you actually had an intact limb. So then the prosthetic user should also be able to use this multisensory information during prosthetic control. That is where we want to get to. And I will argue why essentially in the current state of the art, that's just not the case. So people are not able to use this multisensory information, or it's either just not available to them, or if it is available, it's not available in the right form, and so on. And if we tackle these problems one by one, we should eventually get to a better prosthetic system. So just like we had this block diagram, you can think of the prosthetic control diagram, slightly more complex. But essentially you had the block of hand over there in the middle that gets sort of split into three parts, because now from the muscles you have some human machine interface, which in body powered prosthetics can just be the cable that you're pulling on. There's a Borden cable that pulls the hand to open or close, that's controlled using the opposite shoulder in some cases. So that's the human machine interface. If you're using active prosthetics that are current state of the art, it might be an EMG system, that's electromyography system that's detecting muscle signals and then trying to decode motor intent. You have a bunch of ways to decode motor intent from there. Then you have the prosthetic controller that's actually translating that information that you got from the human machine interface in a manner that's usable for the prosthetic hand, and then you have the actual hand that moves accordingly. And then you have again the environment and the object environment-object interaction, creating that feedback through the haptic interactions as well as the visual and auditory interactions. So why is this important? So limb loss and limb difference is a problem that affects a wide variety of people. So there are millions of people in the US today that actually suffer from some kind of limb loss, most of them being lower limb loss. But there are, our problem, especially in this dissertation I'm going to be dealing with, is majority upper limb loss. It's a very prevalent problem. A lot of people have an amputation every year, so it's not like there's there's this population that's just there and it just ends. We are adding to that population every year. So it is a growing problem. The key point here, though, is that even after years and years of development of these prosthetic systems, it is not a solved problem yet. And why do we know that? We know that because there are quite high rejection rates amongst people who are prosthetic users. So there are these systems designed for prosthetic users that they just don't end up using. They maybe use it for a while, they reject it, don't use it for a long time, or some just don't feel the need to use it. But the interesting part is that a majority of people who are non-users now, when they are surveyed about why they stopped using or whether they would start using such a system again, they do give reasons like there has to be improvement in control or improvement in feedback or so on. There's a number of reasons, but they are willing to restart using their prosthetic. So that is essentially the gap we would like to fill. That if we solve these problems that people are surveyed for, we will eventually get to a system that people feel like using again. So I try to think of prosthetic control in these two parts. So first of all, what is the goal of prosthetic control? And then how has the current state of the art research tried to solve this? So you can break down the goal of prosthetic control in two parts. You have the aim of prosthetic control is either dexterity or intuitiveness of both. So dexterity meaning the ability to perform a difficult action quickly and skillfully, and intuitiveness meaning the ability to be readily learned and used, as in you have a human-machine interface. The question is, if it is intuitive to use and is just presented to you to use this prosthetic limb, how quickly can you learn to use it? So that's the real question. So ideally, we want a system that's very intuitive to use, so people can just take it out of the box and start using it with very little to no training, and they can perform actions with high amount of dexterity, as in they have a lot of control over the limb, they have fine motor control over the prosthetic hand, and so on and so forth. Essentially trying to mimic the movements of the original limb. And researchers tried to solve these two problems essentially by either increasing the mechanical complexity of the prosthetic hand by increasing degrees of freedom. So essentially, back in the day, you had a prosthetic hand that was just a hook and you could not do much with it. Well, I'll come to that later. But then that progressed on to having these just open-close electrical terminal devices that changed now to anthropomorphic hands that actually look like a prosthetic hand, have multiple fingers, multiple digits, and so on. So that development has gone sort of on its own branch, but there's also been improvement in the volitional movement intent recognition. So that answers the question, how do you know what the user is trying to do, and how do you tell the hand to do that? So essentially, you can think of the first point as how well is the hand able to execute the actions you're trying to do as close as possible to the human hand. The second is how does the system know what the user wants to do? So these are sort of the two main branches of development. So when it comes to the actual mechanical design I spoke, so in the early 20th century, you had these body-powered prosthetic hands, largely developed because of a lot of people had amputations around the world wars, so that was a big driver. So you have this body-powered arm, which essentially has just a single grasp, so it can either open or close, and there's a cable that runs from the hand up the arm, and it's usually tied to some other body part, in many cases the opposing shoulder, if it's possible, and the user has to then coordinate movement of that opposing body part in order to close or open their hand. It works quite well, to be honest. And you'll see later in videos, it probably works sometimes better than the active prosthetics that are out there that cost $30,000 to make. But it does have its own limitations as well. It does have advantages because people often, users say that it is intuitive to use. That makes sense because they are actually pulling on a cord that proportionally closes and opens the hand. So they feel that they have complete control, proportional control over the limb. After that, there were these, around the mid-20th century, there's something like this, EMG controlled hand where you have a single grasp, so similar to the body powered hand, but you have myoelectric control. So you're no longer pulling on a cord with that opposite shoulder. You're just thinking of either closing or opening your limb. There are more complexities to that, I'll get to it, but essentially it's movement intent driven. So the user tries to think of doing something, they try to initiate that movement that causes an electrical signal to flow down, causes that electrical signal to be detected in the muscles. That's where the hand picks it up, and then it either opens or closes. Then you have these electrical terminal devices, which are slightly more complex. Similar to the control algorithms are similar to the original electrical hands, but now you have more degrees of freedom. So you could either open or close that wrist, or open or close that that grasper, or move your wrist. You could rotate it. But the problem is it's not anthropomorphic. Now, some users may actually want a hand that looks like a hand. It might be slightly awkward to wear that and do your daily routines. So that then eventually gave rise to what we've been seeing in the last 2 decades. You have these more and more anthropomorphic looking hands that have multiple grasps that interface with these EMG sensors placed on the body. And you have, at least in some cases, the ability to control these grasps proportionally, right? But turns out this idea is actually not very new. So even back in the 16th century, if you see this hand that they found in that was used by one of these German knights, in mechanical design alone and how it looks aesthetically, it's not very different from what we are using now, right? And just a side note is the idea of prosthetics is not new either. So there were these foot prosthetics in 900 BC, right? This is the idea being whoever has lost a limb or a part of the body, the idea that you should use some kind of machine or some kind of artificial thing to replace that is not really new. Then I'd like to focus on essentially this rightmost figure. So we have these hands now that have the capability. So I would say that when I describe the research being done currently, it was either mechanical improvements or volitional intent. Mechanically, they're quite good. So right now we are at a point where a lot of the state-of-the-art control algorithms cannot make use of everything that the hand can do. So the hand can use multiple grasps, individual control of fingers in position control mode and so on. The control algorithms are not able to do that. So one work that we've done in our lab is essentially to bridge that gap. So come up with better control techniques that are able to completely or at best use these hands to their maximum potential. So similar to the mechanical improvement, like I described before, there have been improvements in the volitional motor intent decoding. So what I mean by volitional motor intent is when a user tries to initiate a movement of the prosthetic limb, there are ways in which the system can recognize what the user is trying to do. And that can be read as a control signal from the user at multiple points along that the travel which the signal does. You could either tap directly in the brain or supraspinal areas, which works quite well. There are research groups out there that do this, but then again, this is invasive. This will require you to tap into the brain directly or interface with the spinal cord in some way, which in some cases might require further surgery. And when you consider the point that a lot of these people have had traumatic amputations, they've already gone through surgery and so on, may or may not be desired by users. You could also go to the peripheral nerves. So you could go, this is below the spinal cord. So directly in your arms, you could interface with the nerves that are carrying these signals down from the brain. That could be one approach, but it's also invasive. The third part being muscles directly. So this is the most prevalent technique currently being used even by research groups in some commercial devices as well. And essentially it's using one technique predominantly, that's electromyography, where electrical signals from the surface of the skin are being read and used to decode what the user is trying to do. Now within that electromyography, there are essentially 3 ways of doing this. This is also almost chronologically arranged. So the first picture you see, that's what researchers started to do first. So you either have on or off control. You can either open the hand, close the hand, or not do anything. So it's like saying your car has only forward, reverse, no brakes. So you can control the car, but it'll be really, really hard. But it was the state of the art back then. Then eventually you came to these systems that can be classified as pattern recognition. So you train a machine learning algorithm or an artificial intelligence on these data sets which you gather from users. And then eventually the machine is able to tell what the user is trying to do. The advantage of the second over the first is that you can train the machine to differentiate between multiple grasps. Initially, you had just one grasp, open, close, that's it. Now you could be doing multiple grasps sequentially or one after the other. Eventually, now what research groups have been starting to look at is this regression-based approach, which sort of covers up the shortcomings of the first two approaches, where you're using not only this on-off signal or just the decision that is given by the control algorithm is not just the user is trying to do motion X or motion Y. It is the decision that is given out by the regression system is that the user is trying to do 60% of X or 50% of Y. Now that is more granular information, and that is slowly going towards being able to use the prosthetic hands properly, because the prosthetic hands can be used in Okay, is it better now?
Yes.
Should be, yeah. Okay, fine.
Okay.
Okay. Right. Okay, so based on everything that we saw so far, it seems like there's been a lot of development in multiple areas trying to make the best use of these prosthetic hands, trying to come up with nice and neat, sophisticated control algorithms. But these two videos that we have collected in the lab from very experienced and long-time users of these sophisticated state-of-the-art hands shows that that's really not the case. So if you see the first video, the task is pretty simple. The user is trying to take one of those pins off one of the horizontal bars, move their hand, rotate their wrist, and place it on the vertical bar. So it's called a clothespin relocation task. On the right, they're trying to do something called the box and block. So the task is just to pick up one block at a time from one side of that partition, place it on the other. So there are a number of problems happening here. You can see in the first video, when it turns around, they really lack that proportional control, right? So sometimes you'll see that the wrist just keeps on going even beyond 180 degrees, right? Which is not how a wrist works. So that's really undesirable. Secondly, the user is really having to use their other limb to manipulate objects in their prosthetic limb. That's also really not desirable. So both of these videos essentially show that a lot of development has got us here, but there are a lot of key problems. There is a lack of intuitiveness of control, there's a lack of dexterity, and also there's random noise fluctuations happening in the signal as well. So there's a bunch of problems that can be tackled, right? So when you think about this, the system again, what I want to argue is that if we go into each of these blocks and try to connect or try to design our systems taking into consideration all of these things in a systematic manner, as a whole system, in a holistic manner, then we'll come up with systems that are probably better than what we have today. And the problem with the current systems is that in some cases they have no way of actually integrating haptic feedback, right? So one of these branches is just completely missing. The user then has to rely completely on using their eyes to know where their hand is doing.
some of these feedback loops from the prosthetic hand to the controller just don't exist, or the actual control being exerted by the user is unintuitive. So there's a lot of these branches that are broken in the current control systems. And that's what I want to argue, is that if we make them better, if this diagram becomes more connected, we'll be ending up with better control systems. So my whole dissertation I've broken up into 3 parts. So aim 1 is to characterize the performance of a human machine interface, which I'll describe later, based on ultrasound imaging, which is a specialty in our lab, of forearm muscles. So what I'm going to do in the dissertation is going to break up this block diagram into a bunch of pieces and sort of investigate them separately. So aim 1 is only going to look at the region in yellow, which is essentially going to try and answer, does proportional position based control, which is a desirable thing, enable intuitive control over the prosthetic hand? In aim 2, I'll be looking at how the feedback modalities that are used in the current prosthetic hands, which some of which I've tried to test in the lab, actually enable the user to exert good and intuitive control over the limb. And in the third piece, I'll try to put all of this together and argue of one way of designing such a system. Right. So aim 1. The question here is, does proportional position-based control enable intuitive control over the prosthetic hand? If you dig deeper and try to sort of parse that out a little bit more, essentially it is, how can ultrasound imaging, I'll describe later, can be used to control a prosthetic limb, and what type of control does it allow? So the aim is to answer these 2 main questions. So sonomyography, that's a technique based on ultrasound imaging, is a way of sensing the human motor intent that other people are doing using EMG. In our lab, we are trying to do it using ultrasound. There are some benefits. I'll come to that. So essentially, if you try to think of 2 different motions of the hand, so user is trying to do either an index finger flexion or a middle finger flexion, that will give rise to, so what you see down are cross-sectional ultrasound images of their forearm as the user is trying to do the motions given above. So essentially, even with just your eyes, you can actually tell the difference between these patterns. Right? So you can see a lot of the bright parts move in very different ways when the user is trying to do 2 different grasps of the hand. The goal now is to actually pump this information into a control algorithm on the computer and try to see if they can the algorithm can tell the difference between these 2. Turns out that it can. So here first we have an able-bodied individual who is moving their limb. They are achieving some end state motion of their hand, and then the prosthetic hand is doing or mimicking the same action. Then we tried the same stuff with a prosthetic user. So here clearly you can't see the movement of the limb because the person's limb is amputated, but they are trying to do this motion. They are verbally telling the researchers in the room what they're trying to do, and that is essentially what the hand is doing as well. Just to clear, we are not telling the hand what to do. The control algorithm is doing it. The user is just telling the researchers to make sure that we get the data. Then we have one more example. So you saw the box-in-box task done by somebody using an EMG-based prosthetic before. This is the same person doing the same task, but this time they're using a ultrasound-based control algorithm of the hand. I probably should have had those 2 videos playing next side by side, but essentially the point here is they are able to exert this intuitive control very quickly with very short training, and there are a bunch of other benefits as well. So this user had issues of doing these compensatory movements because they didn't have intuitive control over the hand, so they would move their trunk a lot more to pick up these blocks. That seemed to at least visually go down. But what I would really like to talk about is this video. So here, the user is trying to pick up the bottle. So the instruction given was just pick up the bottle, try to hold it, put it down, right? But you can see that they're proportionally squeezing their hand to raise the water level inside the bottle such that it goes high enough that it goes to the top but doesn't spill out. Right? This was not an instruction. So this user felt confident enough after using the system that they can do this with a hand right there that costs a lot of money, right? So which is a good thing. And if you see, they are actually trying to mimic those movements with the other limb, with their intact limb, which is also kind of interesting. And this type of proportional control is what this dissertation is essentially looking at. Okay. Any questions or comments? No? So on-off control or end-state control has been achieved using other techniques like EMG and a bunch of other ways. But the question is, can ultrasound imaging enable proportional position control over the prosthetic? We saw an example of that in the video, but I'll actually try to show you data for the same. So what I did in this work is had the user wear the ultrasound transducer on their forearm. They have no access of or visual access of what their limb is doing, just an internal sense of proprioception. On the screen, there's a cursor target moving, so they try to follow that. And the user, the X is being actually controlled by the user's extent of flexion. So the more they flex, the more the cursor moves to the left. Less they flex, the cursor moves to the right. Yeah. So essentially, when the user tries to do different movements of the wrist, it results in different ultrasound images that are collected, sent to the algorithm, and a signal is predicted. So now you can try to sort of map these two against each other. You can have the prediction from the ultrasound versus the actual joint angle that we had measured from the wrist. Okay. So if you see that, it's pretty linear, right? And it's not just with one motion, but with three. So I could have had more plots here. So essentially, in my experience, if the user is able to do the motion, they're able to do it proportionally, and we are able to get such a signal for that. So that's sort of the fundamental building block behind all of this work. So then the question naturally is, okay, you can extract this signal and you can decode what the user is trying to do. Can you let them do something meaningful with it now, right? Because this is just decoding human motor intent. Can you allow them to use this to do a task, right? So can this become an input to a human-machine interface, right? So here, this is a short 20-second video of describing what I did. So you just saw this. And as the user is doing this flexion extension, you have a ultrasound image that changes dynamically. That information is fed to a cursor. The cursor moves on the screen, and the user is asked to achieve that red target. The position of that red target changes. The user then has to achieve different levels of flexion to achieve that red target. And then you can actually study how the user achieved that task in order to make some conclusions about it. So for this work, you saw a similar interface before. We asked the users to do a bunch of different motions and do this proportional control over this virtual cursor. And one example of an amputee user using this is given here. So you have the blue cursor, the blue trace, that's the user's intended limb position that's moving. And the black short lines are the target positions. So essentially, we show the target to the user tries to move there, hold there. After a point, a new target is shown, they move to the new target, and they keep on doing this. So one thing is pretty clear from these very low errors and very good stability that the users are able to achieve these target positions with quite a lot of ease, right? And I'll try to get a little bit more into that later. But essentially, this shows that the users, at least with visual feedback to the system, can use the system quite intuitively and quite well with very low errors. Right? Yeah. So if they're able to achieve these virtual targets, can we also say something about the trajectory that they took to achieve these? Essentially, the motivation behind that is to answer this question of, is this machine interface intuitive to use? The question is, can you compare it to something else that is intuitive to use? So we know that just moving your limb in space is quite intuitive for everybody to do. Right? So if I just ask you to move your arm from point A to point B, that's something that everybody can do. Turns out that there is very predictable behavior and movement patterns when I ask you to do such a motion. Right? So then the question is, can you compare the movement trajectories using our human-machine interface to the movement trajectories while the same user is doing a natural action of the entire limb? Right? And if those two are similar, that says something about intuitiveness of the machine interface. So it turns out that if you actually ask somebody to move their limb in space from a defined point A to a defined point B, as the position changes on the left, so does the velocity on the right. This velocity characteristic on the right is very typical. It's called a bell-shaped velocity profile, where essentially the user starts at 0 velocity. As they are moving, they achieve some max velocity and then they slow down towards the target when they get to the end. And the height of this bell curve, that's the maximum velocity that they achieve, is proportional to how much they are moving. So essentially, if I ask you to move from point A to point B, you'll have some max velocity. If I now double the distance and ask you to move from point A to C, that's where that distance is double, the peak velocity that you achieve will be double. So the question is, do we see this behavior in our sonomyography data as well? So the experiment you set up was, everything is sort of divided into these two. You have natural movement and sonomyography. In natural movement, I asked the users to move this handheld manipulandum along a digitizing surface where I could measure the movement trajectories as they did this movement. And on the second, you saw the sonomyography setup right now. Right. So first, the natural movement, this is not surprising at all. So every plot is a different target location. The top row is the position traces, bottom row is the velocity traces. You just saw these before. The black lines are the model minimum jerk trajectory that you saw earlier. The red line is the average trace for all users for all trials, and the yellow region shows the standard deviation around that. So a bunch of things to see here. First of all, this confirms the data in the literature. So that's first. Secondly, standard deviation is quite low, which means across users and within the users, they perform quite similar to each other, right? The question is, would we see similar trajectories when the user is using a sonomyography system as well? And turns out that they do. Okay. So you see all the similar characteristics. So you see a sort of a minimum jerk sigmoidal shape to the position trace. You see a bell-shaped velocity profile. You see a scaling of peak velocities. So the peak velocity on the first plot is significantly smaller than the second, third, fourth, fifth, and it keeps on increasing, right? So another way of seeing this is, okay. So the point of this plot is another characteristic when users perform motions with the minimum jerk trajectory is that you have a systematic delay in the time it takes for them to achieve the peak. So that is what you see in both of these. So essentially the peak of the blue happens before the peak of the red, before the peak of the yellow, and so on. Similar behavior is seen slightly distorted in the ultrasound signal as well, which will be slightly more clear on the next plot. So here you have the peak velocities. So essentially the height of all of those bell curves, I've put all on this plot against the target distance. So the natural movement and sonomyography both show this linear scaling of peak velocity with quite low errors, which confirms the hypothesis. There's also similar scaling of time to target. So the further away you move the target, more time it takes for them to get there, essentially. So it's not like they're infinitely, so why is this? So somebody would argue, I think Parag, you had a question? No, okay, all right, okay. So if they're able to infinitely scale the peak velocity, they would have the flat time to target. So no matter where the target is, you should be able to achieve it in the same amount of time. But users are not able to move with infinite velocity. There's an upper limit. So eventually they're going to try to sort of modulate both of them, time and peak velocity. So one way to look at this is you saw both of these plots, but now essentially you saw the relationship of B versus A and C versus A. So peak velocity versus target distance and time to target versus target distance. You can sort of visualize both on the same. So you have a normalized time to target on the y-axis and normalized peak velocity on the x-axis. The point of this plot is a few things. So first of all, the change in time to target is smaller than the change in peak velocity for both, essentially. So they're changing the peak velocity more than the time it actually takes for them to travel. So that result is consistent across both. You do see increase in both, right? So time to target does increase, peak velocity does increase, just one more than the other. The point also is that sonomyography is slightly more across users. There's more variability in these results, which I would argue comes from a bunch of things. The system is not perfect yet. We are essentially using a metric. The sonomyography control signal is a proxy for muscle movement right now. but eventually we are getting to a point where it will actually measure muscle thickness and so on and actually be tied to an anatomical movement. I think those results will get a lot better then. But it's just essentially a difference between there we are actually literally measuring the movement as though there was an IM Euro tracker on the finger. Over here you're deriving movement. The fact that these look anything like each other at all, I think is kind of an interesting result. I'll skip this for now, I can come back to it later. But essentially what we saw is the time course of these derived trajectories is similar in both the cases. So this shows that sonography could become an input to a human-machine interface. Right? So we looked at the yellow region right now in aim 1. In aim 2, I'm going to be looking at these feedback loops. So how does deriving or giving users access to types of feedback actually affect their performance? So the first question is proprioception alone enough to accurately predict the extent of muscle deformation? Essentially, if I asked you to close your eyes and tell you to go, put your hand out and move your wrist to the exact same angle 100 times, there would be some error. You wouldn't be able to go to the exact same position every single time, right? But now if you're going to base a control system for a prosthetic hand that's based on that signal, that will also have that error. So then the question is, how much really is that error? Right? Can users eventually use this prosthetic system without looking at it? So this is sort of the fundamental motivation behind it. So you see this picture 100 times, but yeah, use a very similar system, but this time divided the task into 3. First, there's a visual target acquisition. So there's a target on the screen. The user moves their wrist to achieve the target. They go back to rest. In the second one, they achieve the target visually, but once they are at the target and the cursor just go away, and they're tasked with holding that position that they had just acquired completely without visual feedback. In the third one, this is the interesting stage where you achieve a target visually, you go back to rest, and then the feedback is completely taken away. So now you're blind, and you now have to mimic that same level of movement again without visual feedback. The hypothesis is that in that last condition, users would be really bad at doing this task. Question was how bad? Was there something systematic we could say about it? So the way to look at this is there was a visual feedback part first before that black line, and then there was the blind feedback part. There's more in the next one. Okay. So if you look at just the middle row. So the first one on the middle row says that the users had visual feedback in both the cases. So you can see that the dotted line, that's the target location. So the users are very, very tight to the target location, essentially because they could see where the target is, they could see where their cursor is, and they could manipulate their cursor to achieve the target. So that makes sense. We've seen that many times before. The second and third are the interesting cases, because in the second one, the users achieved the target visually. Once they got to the target, the visual feedback was taken away. So it seems like some users actually drifted off the target, right? And which is interesting because now it tells us that even if users have, say, grasped onto something, it's not necessary that they'll be able to hold on to that same level of flexion. Now they have grasped onto it. Yeah. And in the third one, this is all over the place because here essentially the users were trying to recreate the position in the line beyond the black trace that they had achieved before the black line. Yes. This is the black trace is amputee user, and everything. All the other colors are able-bodied. Yeah. And then so a lot of plots, but I'll just talk about the first few. So on the first one is essentially the important one. So that's essentially how much error on average did the users have with respect to the target in all these different conditions. So you can see the first one is just visual target holding. So they had visual access to both, the errors are quite low. Then the errors slightly increase when the users are at the target already, but now they have to hold on to that target without looking at it. But they increase significantly when the users have to achieve a target without even looking at it. Now the third condition is like trying to grasp an object without looking at it, right? Yes. So the bottom row is amputee, top row is able-bodied. Sorry, yeah, good, thank you. So the question is that purple violin that has a lot of error, can you reduce that error using some type of other feedback that is not necessarily visual? Why not visual? Because currently prosthetic users have to use their eyes to look at what their hand is doing. We want to let them not have to do that. Right? So can you use some other type of feedback? So then I tried to look at whether users would actually regain their performance when provided with relevant haptic, event-based haptic feedback. So when they touch something or they do something that is relevant, induce some haptic feedback through some vibration or something and give that information to them, will that actually reduce those errors in that purple violin at the end, right? So very similar setup, but this time the users actually wore a cuff or a band that had small vibration motors that provided vibration depending on what the users were doing. So what you see is the red violins show the data where there was no visual no haptic feedback whatsoever. So the same three conditions from before, you see the same result, that when there's visual holding, I'm talking about just the red data, right? So error increases from visual to blind holding to blind acquisition, and the green ones are where they had visual had haptic feedback now. So there was a vibration provided whenever the error increased beyond a certain limit, and it was proportional. So the more the error, the greater the vibration. So it turns out that users can actually use that information to lower their errors. Some interesting things is, if you see the entirety of the data in the green on the last violin is above 0, which means the users actually, so above 0 means they were holding the target, like they were above the target. So the equivalent would be holding on to the object. Below 0 would be dropping the object or not making contact. So if this exact system was a physical prosthetic system, what this data would tell me is the users would rather have access to a vibration or some type of feedback and know that they have an error than they would drop the object, right? Otherwise, we would have seen similar distribution both below and above 0. And if you look at the stability, there are not significant differences here, but the main point is the actual stability of the control that the users exhibit does not change, meaning they do not jump around more because they have more or less feedback. So that seems to be a completely different phenomenon that is not essentially dependent on feedback, right? And I'll get to that as well. Then one sort of additional question is, so this is sort of analogous to the first part that I did using just these endpoint target acquisition tasks. But I also looked at the trajectories earlier. So because I argued that the movement trajectories and the nature of them actually tell you something about the intuitiveness or naturalness of a control system. But the question was, those tasks were entirely done with visual feedback. So the question is, when I try to move my limb in space, yes, there are typical trajectories that I follow, but is that the product of something that is internal to me that I would not have been able to change? Or is that the product of me having visual feedback to my hand? Is that a product of the interaction between my visual feedback and my motor system, or is it something independent of that? The results that I'm going to show are preliminary right now. They're being written up and so on. It's in discussion stage, but they are promising. Okay, so what I would expect is I did the same experiment, but this time I did one trial with visual feedback, one with no visual feedback, right? For both these experiments. So both limb movement in space as well as just wrist rotation. My hypothesis would be that yes, minimum jerk trajectory would be followed in both of these cases. Okay? Just that the error would be slightly large when the user has no visual feedback. And that's exactly what I saw. So when I say error, I mean the distribution across trials is larger when there is no visual feedback compared to when there is visual feedback on the top. You see this this is for the natural movement, able-bodied. This is for the natural movement for an individual with limb loss as well. So here the user is, the person with limb loss is wearing their prosthetic limb, holding something in their hand and moving their limb. Okay. You see the same traces for sonomyography for an able-bodied subject as well as sonomyography for an individual with limb loss. Now this is where the interesting stuff begins, and I want to go deeper into that later. And similar to what I saw before, here you have this peak velocity mapped against the target location on the screen. The light violins, the light colored violins are the able-bodied subjects, the dark colored violins is the amputee user. The point of this is that both of their behavior is quite actually like each other. You see the scaling of peak velocity that's linear with respect to target movement distance. So sonography derived movement trajectories followed the MJT model even in the absence of visual feedback. And I'm going to go deeper into that later with that paper. And now, so we looked at this, the feedback modalities and how that affects control. The last little piece is putting all of this together. Right? For that, any questions? Or? Okay. So if you think about how you actually control movement, this is a very high level understanding of how movement in the limb is controlled. You have some decision being made in the brain that's being fed through the spinal cord, through the motor nerve, to the muscle. That muscle actually flexes or extends, right? And then that limb moves, interacts with the environments. The sensory organs in blue actually sense that information. They can be mechanoreceptors or some other type of sensing that is fed back to the spinal cord and from there to the brain. If you think of an amputee user, this works fine in an able-bodied person. We use this exact same system all the time. But if you think of a prosthetic user, some of these parts are missing. So they may still have control over the red. So the brain is still creating the motor command that's still going to the spinal cord through the muscles that we are detecting using, in our case, sonography, other cases, EMG. But the hand is actually not sensing much. Okay? In some cases, even if it is sensing, it's not actually feeding it to the same pathways to the spinal cord such that it can relay it back to the brain. So that system is broken. The question is, can you actually now replace this in some interesting way? So one proposition that people have done in the literature is to use shared control. So essentially offload some of the control to the onboard computer, where the computer will read that information from some sensing, some sensor on the fingertip of the hand or something like that, and use that information to drive the hand again. I've tried to give one example of that, and later on, if there are questions, I can go into why this specific way of doing shared control is different than what people have done in the literature. Okay. So the setup is on the left. You have a user using the transducer, or the ultrasound transducer is strapped to their forearm. That is going into an ultrasound machine that is feeding those images into a computer. The computer is generating the control signal that's going to the prosthetic hand. The hand either opens or closes based on the user's commands, and then you have a cylindrical object that's hanging from the ceiling that the user is actually trying to grasp. Okay, so the red line is a thread. That is not clear. You also have the top view, just to make it a little bit more clear. The small white thing that you see on the fingertip is the force sensor that the computer is actually interfaced with, that it can use to sense how much force is being exerted. So the way shared control would work is the user achieves some level of flexion, the hand moves to that appropriate position that the user wants it to move to. Then when it eventually makes contact with the object, right, it will keep making contact with the object so long as the user command does not change significantly. Now, why do this? Because we showed earlier that users are able to use a prosthetic hand to hold on to objects, but they have to keep on looking at the object while they are using the prosthetic. We don't want that. We want to offload some of that quote unquote intelligence to the prosthetic hand. Now, this is one very crude attempt to do that, right? So essentially, the system will keep on monitoring what the user wants to do in the background. As long as that intended command does not change too much from what the hand is doing, it will keep on holding that hand grasp. And that's one way of implementing shared control. Okay. So I had 5 conditions. First condition was no visual feedback. So you couldn't see the hand, you had no shared control, you had no haptic feedback. So you were just blind completely. So that's sort of the base case. Then you have a visual feedback case where the user can see the hand. There is no shared control and no haptic feedback. So this is what prosthetic users currently do with their current hands, right? The third one is haptic feedback, where they cannot see the hand, they do not have shared control, only get a vibration once they make contact with the object or once they drop the object. Okay. The fourth one is shared control. So that's what I just described. But there's no haptic feedback during that, and they have no visual feedback of it. It's only shared control. Okay. The fifth one is where I think we should go, and what hands should be doing is haptic feedback plus shared control. As an implement shared control, but once you make contact with the object or lose contact with the object, also alert the user using haptic feedback so that they don't have to use their eyes now to monitor the situation. So that is where I would ideally like to go, right? You can sort of think of these results in a bunch of ways. I calculated the target completion rate. So this is essentially how many of the objects were not dropped during this trial, right? So you can see that clearly for the no feedback condition, it's quite low. It would be surprising why it's even this high. I would say that it's because the users just maximally extended their hand or their forearm muscles such that the hand would just squeeze the object and hold on to it. So I would change this experiment slightly if I did it all over again. But yeah, that's what the result was. Then with visual feedback, the result becomes slightly better, which makes sense. With haptic feedback, it becomes slightly better than visual feedback. There are details there and nuances I can go into if anybody has questions. But the interesting part is that shared control and haptic feedback plus shared control actually outperform all of these other modalities. And you'll see a little bit more detailed results now. So this is what I was talking about. Now you have force on the y-axis versus all these conditions. So naturally for the no feedback condition, the users just extended highest amount of force that they could and just relied on that. Whereas you had very low force for the last two conditions, that shared control and shared control plus haptic. Actually, this is not. Yeah. But at the same time, what we also did is, what do we eventually want to do with this? Like, where does this go, right? Or what does this improve? I would argue that such a system that has shared control and haptic feedback should improve or reduce the cognitive burden on the user of having to look at the hand, having to constantly think about what they have to do, and so on. One way to measure cognitive feedback is to use this scale that NASA's put out called NASA TLX that sort of breaks down the cognitive feedback on these 6 different axes and asks the user some questions after every trial to get these numbers. Okay. The first one is mental demand. This makes sense. So the mental demand for no feedback was completely low. The user had no idea what they're doing. There's no stress whatsoever, right? Visual feedback and haptic feedback actually induce more mental demand because now the user, even though they have information, seems like they have too much information, that they have to constantly think about what they're doing, what their limb is doing, are they maintaining the right level of flexion, not dropping the object, and so on. The last two are promising because now you're reducing the mental demand while still delivering the performance. So that's the benefit of it. The physical demand, again, makes sense. This should have correlated with the level of force, which it does. So the more the force, the more the physical demand. Temporal demand was essentially flat, which makes sense because in the specific task, there was no need for the user to complete the task within a certain time. We didn't like, oh, now you have less time to control the same task or anything like that. So this effort, the performance, so this is the interesting part. So what performance means is that to ask the user, how well do you think you did on this task? Okay. For haptic feedback plus shared control, it's very high. For no feedback, makes sense. They had no idea what they're doing. It's very low, right? But haptic feedback plus shared control is actually better than just shared control, which again makes sense because they got a vibration when they did better and held on to the object. Right? And the frustration level was also quite low. I would argue it's quite low across the board. So like that's not the important part. But from all of these 6, how do you put this together? So you want a system that the user has a good gauge of performance for, that does not induce high mental and physical demand, and the user does not have to take too much effort. If you put all of this information together with the force information on the previous one and how many trials they completed and so on, and everything that we've talked about so far, haptic feedback plus shared control is the option that makes most sense. And we can talk a bit more in the questions. So that was aim 3, where I looked at a shared control scheme that reduced cognitive load while retaining performance. Okay. So just to summarize, in aim 1, I just look at the human-machine interface and how users can use such a human-machine interface by removing the prosthetic hand from the loop, but just abstracting it into a virtual cursor control task to characterize performance of users. Then looked at the individual feedback loops as the user was controlling these machines, and then put everything together and proposed a shared control algorithm that I think should be used. I would say so there are some main findings. So sonography can track joint kinematics for multiple hand gestures. I would say that that comes out of some work that was done before me in the lab as well. I'd like to thank some other lab members for that. And sonomography can enable proportional position control in persons with amputation. Those are the videos that we saw. Then the control trajectories derived from muscles while using position control reflect natural movements of the human body. So this was the bulk of the work that we saw in the middle. And visual feedback is highly important, but can be somewhat replaced. But however, when you replace visual feedback with something else like haptic feedback, the cognitive load actually increases. And one way to reduce that is to use shared control. So that sort of ends it. And I would say the main contribution of this dissertation is a detailed unified framework for design of control as well as feedback strategies in the same loop. Because currently these systems are being developed disparately by different research groups in different labs, all doing excellent work, but they may or may not be talking to each other and making best use of each other's capabilities. And these are the publications that came out of it. And yep, that's all. Thank you.
All right, at this time, we are open for questions from our audience. After those are done, then we'll have a closed session with the committee. So if committee members have a follow-on question based on that just happened, that will be good. But if you want, I'll defer to you.
So there are not many questions on Zoom yet, so we can do the Zoom and then maybe give some time.
Anybody who has any questions, feel free to ask us now.
Yes.
I have two. One is a clarification. In the last set of slides, 16, the shared control.
Yeah.
69, the shared control condition, they still have visual feedback, or are they blinded?
For just shared control, they have no visual feedback.
Okay, so they're just trying to grasp and letting the hand do.
Correct. So this is this, right?
Yeah.
So just shared control has, sorry, they had visual feedback. For yes, sorry, yes, you're right.
Okay. So my other question with shared control is, does it require the proportional?
Good. So yeah, that was the nuance I was talking about. So currently there are algorithms out there that use shared control with pattern recognition. We don't use proportional control at all. I would argue that this is a better implementation of that, right? So because what happens in shared control? So you know that, say, this is the object you want to grasp, right? In pattern recognition, the way to grasp onto that object is to imagine a motion, right? The user imagines that motion, the hands begins to close. The user has to hold on to that motion in their head as long as they want the hand to keep closing, right? Then eventually the hand will make contact, the hand will engage shared control, not leave the object or drop it. In the background, what is the user doing? Right? The user has completely left the idea of that motion from their head, they are at rest. This, even though from a task completion point of view, might be fine. They didn't drop the object, shared control did its work. But now what happens when they have to unengage? Right? So there are some benefits to position-based proportional control, which is intuitiveness. It is aligned with some of your proprioception. You know what your hand is doing at any time without looking at it, and so on. I would argue that this implementation of shared control, which is based on proportional control, actually keeps the benefits of proportional position control without, or keeps the benefits without or by removing the cognitive load. Because everything is there for position control that is not for pattern rec, but it adds cognitive load. That's the main problem. So when you have position control as opposed to pattern rec, you have all these benefits of it being close to your proprioception and so on. You think then other things as well, but you add cognitive load because now you have to keep on holding that grasp, you have to keep on thinking about it and so on. Essentially what this work does is allows the user some leeway. It says, okay, if they have to hold this object, you could be somewhere within that range and still hold the object, but you will still maintain a sense of proportional control over the hand. Because if you completely change the proportional signal, the hand will still disengage. Does that answer your question or no?
Yes.
Okay.
Can I ask a follow-up question? So can you so go back to that master PLX plot? So how does this numbers match with what the
Oh, so with the shared control literature, I don't believe they have the NASA TLX course. They may have done, so they have done like EEG recordings and things like that. At least to my knowledge, there's no work doing like NASA TLX with shared control on off, things like that.
What about performance?
As in?
Trying to see, quantitatively it makes sense. Is there evidence that we can compare to the literature to back that up?
Yeah, so I think there are a bunch of confounding factors here, right? So so when you say performance metrics, you mean these, right? So I would say that the two main important ones are the target completion rate and the force. So there is a level of control which you can have over the hand, which will allow you to have very good target completion. The reason I think it makes sense to not only look at these, but in conjunction with the NASA TLX, is because they tell a story together. Because somebody can be very, very good at a target completion rate. People can get very good at a box and blocks task. Does not mean that the system is intuitive to use to somebody who is a naive user. Right? Like we've described many times, people can use a hook to wear their socks just fine, like an expert. But does that necessarily mean that a hook is more intuitive to use than what we envision the prosthetic hand to become one day? I agree that the prosthetic hand is not there right now. So if you gave that same user an option, do you want to use this bulky 5 kilo thing that doesn't work, expensive, or this hook that you can actually use to do meaningful things? I'm sure they'll use the hook. But I think it has more to do with the hand not being made properly enough, the control not being there, and so on.
In your study, are most of the participants a single hand amputee, or do you have dual amputees?
So that in M1 they were mostly unilateral. The last.
Do you find that people with both hands amputated can't perform as well? Or they don't learn, it's not as intuitive?
So I would say there's again some first of all, it's very hard to get data on prosthetic users, so that's first. And usually you don't get these nice clean cut conditions. So for example, the bilateral amputee that we collected data from is also congenital amputee. So now if they say have a lack of performance, how do you know where it came from? I would ideally like to collect this data from 10 people who are just unilateral, traumatic, all these conditions. So it's very hard to answer that question.
The reason I ask is because I was struck by the video where the person was using their intact to perform the same task. Right? So I wonder if they're essentially using that as a shared control.
Yes.
Because they have visual input on that intact arm and they have haptic feedback from it, even though they don't have visual feedback with active arm. This could essentially function as shared control.
Yeah,
so
that's
if you block them from
interesting.
seeing that intact arm, does their performance drop?
And we can do that experiment. That's a great idea, because that specific user actually, when they were training, they told us that they do not have the sense of what my amputated limb is doing. It's not that great. So they just said, can I just use my other limb to sort of know what this forearm feels like and mimic that on the limb? So that's how they think of motions.
Or if you change your task to say, you either do it with just one or you do it with both.
Yeah.
Right. So, because when you do proportional control with your intact arm, you get feedback.
Right.
So you get tension in your forearm. You could possibly use that.
Yeah. So the argument is that they are probably using that right now. That's why they have this nice proportional control over the limb. But yeah, that's a good point, to actually blind their intact limb.
Or just scrap it. Don't let it
Yeah.
use.
Yeah.
Good point. So when people in the audience ask you questions, could you repeat them? Because now
Oh,
this is the only mic
sorry.
catching the questions.
Okay.
And then we have a couple of Zoom questions. So
Okay.
whenever you're ready, they're sent to me, so I can.
Okay. So there's the first one is, can you elaborate on the nature of the algorithms used? So interestingly, so that's another, I would say, benefit of ultrasound. So far, the algorithmic development used in this work is not that complex. So almost all of the work that I shared here, and by algorithm I mean how do you get a control signal from the ultrasound image? That part is done using a first, the classification part is done using a KNN approach. The proportional signal is actually, it's ridiculously simple to compute. So you literally take the incoming ultrasound image and you compare it to the ultrasound images in your library and you say how similar are they. So you know that what wrist flexion extension ultrasound image looks like, you know what a power grasp looks like, index finger looks like, and so on. And you just compare your incoming images in a 2D correlation to that, and the value that you get out is your proportional signal. The argument, the sort of theoretical reasoning why that works, I think, is because the closer you get to the intended motion level, the higher the correlation between that end state and you is. So that's why it works proportionally. Do you think that prosthetic devices should be fundamentally designed to mimic or replicate human behavior, or do you think prosthetic control strategies should exist in their own class? It's a very Samuel question. But no, I think that's a good question, Samuel. So I was of the opinion that the prosthetic hand should, in the limiting case, operate exactly like the intact limb. And I've changed over the course of my PhD, I think, slightly, because this may be a user-driven thing. Because I have spoken with people who do prosthetic development and control algorithms for a living, who hate the idea of calling their prosthetic hand their hand. They think of it as an attachment to their body, and that's what they want. On the other hand, there are some users who actually want a very nice, real, lifelike, very naturally moving and so on prosthetic hand. Some people like a hook. Some people, there's a wide variety between the users and their opinions. I would say the job of us here should not be to dictate what that choice should be. It should be the job, like our job is to actually ask what the user would like to do and deliver the engineering system that would best achieve that goal. And if we can get there, then so be it.
There's a couple of questions here. Is there any data to compare between amputees and individuals born without full limbs, without both limbs?
So like people who have had traumatic amputations and people who are congenital. So I would say yes. In our data set, the one that I showed before, we had a person who is a congenital amputee, a person who lost their limb when they were 9 years old, and also people who had traumatic amputation very recently before the studies were done. There was no significant difference between actually their performance, which again could be different for different people. So, I mean, there are subjects who, for example, there are subjects that I've spoken to who have used these systems for so long, like the traditional electromyography systems for so long, that they have just not used the idea of this proportional control for like 5 decades. Right? It may be hard to get it back. It may be easy. We don't know. In one of the subjects we tried, it was very easy. In 5 minutes, they were able to reimagine all of these movements again. That may not be the case for everyone. So this is like one of those things that I think we really wouldn't know till we have like literally hundreds and hundreds of these data. Nima has a question. Have you ever considered the ultrasound image signal as feedback to the subjects? Yes. So beyond the prosthetic work, what I've been thinking also of is, the reason I frame this as not just a prosthetic control or how to move a prosthetic hand kind of problem, as a more general human-machine interface problem, is because I think what we have here is a good human-machine interface, irrespective of whether it's used for a prosthetic control system. Because at the end of the day, what are you doing? You are measuring some movement in the muscles using ultrasound imaging, which ultrasound is really good at, and deriving some metric based on that. What you use that metric to do is up to you. In this case, you use it to control a prosthetic limb. You could use it to just show the users how their limb is moving in space. That could be useful feedback for them. There could be users there could be stroke users who just want to, do the same repetitive movements over and over again. We could enable that. So you could think of this as a general human-machine interface to just give feedback to the users.
Celeste has a question. Are there any other contexts to which these findings might apply?
I mean, yeah, so the allied work with this that I think is going to take this work forward is what Ahmed and others in the lab are doing. And I think Nima and Anand are on the call. So yeah, people who have contributed heavily to this are here. So the next part would be to actually do all of this with a wearable system in real time when the user is moving. Like that would be the real deal. And if you can actually do that, like essentially, I mean, anybody who's familiar with EMG knows there are wearable EMG systems. People can just wear a brace that measures EMG recordings from the surface of their skin. Maybe we can get to that with an ultrasound system. So you have access to these signals as the user is moving in real time. Then what you use that control signal for is really up to you. You could use it for gaming. You could use it to monitor health. You could use it to monitor movement, recovery, rehabilitation, a lot of things. With this being an intuitive system, can patients calibrate their own motions, or are there set motions that need to be established first? Okay, so both. The drawback of currently existing systems is that a large data set is required to actually train the algorithm. So the approach that a lot of folks take is to train the algorithm separately and then let each user use it at a separate time. One of the good points that ultrasound delivers is the actual signal to noise is quite high. So you don't actually need that much of data to make your algorithm robust. So what we have at least done in our case is just have each user come in, perform these motions. It takes like 5-10 minutes and the algorithm is trained. That's it. So yes, we do train it from person to person.
Brumil is asking, have you explored any implementations for people with movement disability like Parkinson's?
Yes, so I think this ties in with the work before, not just Parkinson's. I mean, this could be used for any condition where you have a movement intent that you want to detect. And that can be used, I can think of it being useful in almost every kind of movement disorder, Parkinson's, CP, whatever you can think of. So with the shared control and haptic feedback, could it eventually lead to muscle memory for prosthetic user athletes? Could prosthetics eventually help people with degenerative diseases even without amputation? Yeah, I mean, I don't think this work shows that, but I do have reason to believe that this kind of techniques that we are developing in the lab that extract position-based signals from the user's intent will eventually lead to that. I mean, I think it will take an entire PhD to look at each of these issues, but I think it's doable. Fundamentally, I don't think there is a reason that it's impossible. I think that it's possible. There's a lot of questions. I want me to go through everything. Okay, sorry. Yes.
In this graph, why do you think the target completion rate drops for haptic plus shared control? Ever so slightly.
So that I would say is okay. So why does the target completion rate drop for haptic plus shared control than shared control? Because in one case they had haptic feedback, in the other they had visual feedback. So even with shared control, there is ultimately a boundary beyond which you will drop the object, which is still easier to process with visual feedback than with haptic feedback. But I don't think those differences are that large. I mean, the real differences are compared to the other modalities, because that doesn't show up everywhere else. If there was a significant difference in, like, fundamentally over there, I would expect to see it across the board, in like every single metric. Any other questions?
We actually had a comment about the Parkinson's question was actually quite interesting because the signals coming to your muscles are already messed up, right? So if you're using ultrasound, your algorithm would just mimic the Parkinsonian movement. So does your algorithm have flexibility within it that you can build in corrections? Because the way I understand it is that the reason it works so well is that there isn't much of a training technique, right? So you just put it on an individual, and every person might have slightly different stubs. Or, I don't know what the correct term is, but you know, the ultrasound will just detect whatever it detects, and then you can code it. So build in a correction.
No, so when I say it can be used for people with Parkinson's, I don't think for a system like an exoskeleton for control. No, because there it would suffer the same problem you're describing. You're measuring the Parkinsonian movement, so there's no point in that.
Pick up some intended movement.
Yeah, so the way I would envision using this in Parkinson's specifically is to actually measure tremor, for example. So can you quantify the level of tremor based on the level of muscle activity? And is that going up or down based on medication, therapy, and things like that? So not as a control technique, but as an objective metric more. Yeah, but you're right. In conditions where the muscle movement itself is degraded or changed in some way, ultrasound is going to measure muscle movement. So, but you could then study the EMG that's coming down. Correct. So you could. I mean, that's. I think the real. Not very. I mean, that can be a whole Pandora's box I can go into, but essentially there are limitations there with where you sense from. If you sense from the skin, there are a lot of problems with noise and loss of contact and a bunch of problems. But you could then say that, okay, I know what EMG signal came down and it resulted in this instead of this. Yes.
Before we go to that question, I would suggest that we
Sure. Awesome.
In an ideal implementation of the shared control paradigm, would you be looking at shared control which is motion specific or shared control for each specific digit of the prosthetic leg? So like, where do you think this should go?
So, okay, so where do you think shared control should go? Do you want to make it into a motion specific thing or an individual finger digit control thing? So there is a realistic answer and there's an ambitious answer. The realistic answer is motion dependent because I know that we can do that today. Right? The ambitious answer is I do think eventually it should be possible to get to proportional simultaneous control over multiple digits independently. I know there are Ahmed and Ananya and Nima will probably smirk at this, but I think not just ultrasound, other techniques. I mean, we should be able to get there eventually. And if you can, then everything you use with like shared control should interface with that. I mean, that's the way you use our hand, right? You don't say, oh, I have this way of closing my limb and I have this way of moving my wrist. You think in terms of individual fingers. So, because you change that configuration based on the size of the bottle. That's what prosthetic users should be able to do. But when we do get there, we'll have the opposite problem because we'll be outstripping the capabilities of the mechanical prosthetic hand. Right now, the prosthetic hand is more advanced than what the command structure is. But that's a good problem to have, I think.
Any other questions from the room, or we have one last question?
So, I mean, are there fundamental differences between able-bodied subjects and amputee users? I think that question is more complex than what I can answer with the data that I have. Because those differences, what I can answer is an algorithm trying to decode movement does not see differences. I think there are differences, or there are probably differences upstream somewhere. There are probably, if you had like concurrent EMG recordings, if you did motion capture, if you did all of this, if you asked for their cognitive load, if you subjected them to a dual task paradigm and measured their performance, like there might be differences. We've not done that. As far as I know, there is no fundamental difference, and the techniques, the way they are based, the sonography techniques, the way they are structured, I don't think there will be any difference. As long as the user is able to do a mechanical deformation of the muscles, the algorithm doesn't know whether it's an amputee or able-bodied subject. It's just measuring how much deformation and what does it compare to relative to the training set. That's it. Yeah, so yeah, that's all. You mind if I just acknowledge everybody in like 2 minutes? I wrote it down. Stop that for a second. This is performance anxiety. Oh, yeah. So it's just going to take me a minute. I'm just going to read it out. That works. So it has taken a large village to get to this point today. And I'd like to thank my committee members first, Dr. Siddhartha Sikdar, Dr. Parag Chitnis, Dr. James Thompson, who I think is still on Zoom, and Dr. Wilsaan Joyner for their positive and negative feedback, frequent intellectual stimulation every 2 weeks, and for replacing my rose-tinted glasses with scientific rigor, hopefully. The time spent at BMIL, especially with Bishwarup Mukherjee, Ananya Dhawan, Ahmed, and Joe, I put your name in there, debating about all things under the sun is going to remain with me. Ahmed's soldering and coding abilities have contributed significantly to this work. It cannot be undermined. Outside of BMIL, I truly value the mentoring provided by several members who I shared my thoughts with routinely, including John Schofield, who was, I think, on the call, and of course, Dr. Joyner. Alongside the technical aspect of things, my strong support systems have been of critical importance. Anvita has been ever-present bouncing board for my ideas, as well as the most dependable person I could have asked for. I thank her for lending a patient ear some rock-solid confidence boost from time to time, which I do frequently require. And it is the best thing that I could have asked for. I would also like to thank Soumitra Thorat, who's also here today, all the way from London, for indulging in all my favorite activities from a million miles away over Zoom. I'd also like to thank my family from back home. My mom is here in the audience today, but also the rest of the family for giving me a grounding in all things that are real in life. And lastly, I would like to thank Siddhartha for being a selfless guru to me, sometimes with an iron fist and sometimes with a small nudge. He's always guided me in the right direction for me. He reaffirms my belief that being a bright scholar and being a bright and good human being can go hand in hand. Thank you.